The next part of the second lecture has to do with large numbers, scientific notation on the different types of numbers we encounter in chemistry. So scientists, we deal with very, very, very large numbers and very, very, very small numbers. So for example, something we'll use very often in chapter 6 will be the speed of light. Right? The speed of light is 300 million meters per second. That's a really large number, right? I would hate to have to write that out over and over and over again. And so one thing we would do, instead of writing it out as 300 million and writing out all those zeros, you could express this in scientific notation. So two ways we'll see this in scientific notation. You could see the speed of light as 3 times 10 to the 8th meters per second. And then a way you'll see this in Top Hat quite a bit is using the E notation, so 3 e to the 8th meters per second. Both of those mean the same thing. Both of those mean that we have 3 times 10 8 times, right? So 3 times 10 times 10 times 10 times 10. There's 4, 5, 6, 7, and 8, right? 3, if you took 3 and multiplied it by 10, 8 different times, you would get the speed of light. You would get 3 times 10 to the 8th meters per second. So both of those notations, both of the ways of writing it, are correct. Both of those mean the same thing, and as you can see, it's a lot easier to write 3 times 10 to the 8th or 3e8 to indicate, right, I have 300 million, and then, yes, we cannot forget our units, so I need to indicate what am I measuring? Meters per second. Similarly, we measure incredibly small things as well, and so here's the mass of an electron, right? I don't even want to count how many zeros are there. So an incredible number of zeros are in this measurement for the mass of an electron in kilograms. And again, we can use scientific notation to represent really large numbers and really small numbers. And so this number turns into 9.11 times 10 to the minus 31. You can take my word for it that there are 30 zeros there in front of that number. And I can't forget units, so kilograms on this. Again, I could write that in 10 to the minus 31. I could also write this as 9.11 e to the minus 31 kilograms. Both of those numbers mean the same thing. Both of these numbers mean this number right there. And again, I'm just using this notation because it's easier to represent an incredibly small number like this. Instead of writing all those zeros out and having to count all those zeros, we could just say 9.11 times 10 to the minus 31 or 9.11 e to the minus 31. I added the e notation here because most of the questions in Top Hat, all the questions in Top Hat that you have to answer in exponential notation, they will provide the answer in e notation. They will require the answer in e notation. And so let's practice that scientific notation a few times. So for example, here are just a few example numbers thrown out there. The sun is 93 million miles from Earth. Express that in scientific notation. So 93 million, so I want to move, right, this decimal place that's right here, I want to move that all the way up so I've got the smallest number possible. So 1, 2, 3, 4, 5, 6, 7. I want to move that decimal places 7 places to the left. So my answer would be 9.3 e to the 7th. Or you could say 9.3 times 10 to the 7th miles. So both of those would be correct answers. Another example of a really large number. The moon is estimated to be, 4.5 billion years old. express that in scientific notation. So again, I want to be able to take this decimal place, that would be right there, and move that 1, 2, 3, 4, 5, 6, 7, 8, 9 places over. So to express that in scientific notation, I would have 4.53 times 10 to the 9th years, or in E notation, 4.53 e to the 9. Both of those answers would be correct for expressing, the age of the moon in scientific notation. Now let's try a number that's smaller than 1. The width of a human hair is measured to be 0.000017 meters. Express that number in scientific notation. So we can do the same thing. Just count how many places I want to move that decimal place. So 1, 2, 3, 4, 5, and 6. So to express that in scientific notation, I would have 1.7 times 10 to the minus 6 meters. Or I could just say 1.7 e to the negative 6 meters. Both of those would be correct, and both of those equal this number right here. Again, scientific notation is just our way of helping us write really big numbers and really small numbers in a much easier way to keep track of what we have. While we're taking measurements in chemistry, we're going to come across two different types of numbers. We're going to come across exact numbers and inexact numbers, or measured numbers. Exact numbers, they are defined or counted. Defined or counted numbers. And it's important because they have no impact on the significant figures. And we'll get to significant figures in a little bit. They have no impact on significant figures. An example of an exact number, right? I could, for example, I could count how many people are in class. So number of students in class. Right, I could count how many pages are in a book. I could count how many seats are in a room, right? All of these are examples of exact numbers, because I'm going to count that exactly. I'm going to know the exact number, right? We have 12 students in class. We don't have 12.5, 12.1. We don't have 11 and a half, right? I can count exactly 12. And another example, those are counted numbers. An example of defined numbers are things, right, like 1 dozen equals 12, right? We all know if I said I had a dozen eggs, we would know I had 12 eggs. So that's, by definition, a dozen contains 12 things. 12 exactly. It doesn't contain 11 and a half eggs. It contains 12. Another thing that would be a defined number, right, would be like 1 mile. For example, that equals 5,280 feet. That would be an example of a defined number. Or that 1 pound equals 454 grams, right? We've defined those conversions. So those have no impact on the significant figures of a measurement because those are exact numbers. I have 12 eggs exactly. I know that exactly. I know a mile has exactly 5,280 feet. That's much different than an inexact number or a measured number. And that's any number that will change depending on who is making the measurement and the equipment they're using. And the instrument being used to make that measurement. These will have an impact on significant figures. These numbers will have an impact on significant figures. So an example, right, of an inexact number, right, we could say the distance, right, distance across the room. I could give one person a little ruler that's a foot long. I could give one person a measuring tape. I could give one person a laser that would go exactly from one wall to the other and tell you the exact distance. All three of those people are going to come up with a different answer. You could, the height of a person. You could do the same thing. I can give you 3 different measuring devices, and they would all come up with different answers. Or weight. You could use a scale from your bathroom. You could use an analytical scale. You're going to come up with a different answer for each of those because you're using a different instrument to make that measurement. And if you're having a different person make the measurement, they might interpret the result in a different way. And that's where error comes up in these numbers. So exact, they're defined, they're counted. Inexact are numbers that you're going to take and make through a measurement. The other 2 things when talking about numbers that we need to talk about, precision and accuracy. So ideally in science, we would like to do both. We would like to have all of our measurements be precise and accurate measurements. So precision is basically how close all of your measurements are to each other. So in science, we don't usually just make one measurement and say, that's good enough, I'm done. We usually try to make 3 or 4 measurements to make sure that our first measurement, our second and third measurement, they're reproducible, they're close to each other. And that's what we're looking for in science, is precision. So how close all of the measurements are to each other. And this is within your data set, the data set collected. So yes, we want all of our measurements to be relatively close together, but we also want them to be accurate. We want those measurements not only close together, but we want them close to what is the accepted value or what is the true value for this test, for this experiment. So accuracy tells you how close a measurement is to the accepted or true value, right? And in an ideal world, right, in science, we would like to have both in our measurements. And so both of these definitions might seem a little abstract. It's a lot easier to look at a picture and just think about what this means for precision and accuracy. And so a good way to demonstrate precision versus accuracy is to think about a dartboard. So imagine, right, we've got 5 darts that you're going to throw at each of those targets and what that would look like for choice A, B, and C. So for the first one, choice A, we're just warming up. Here are your 5 darts. We got to throw 5 darts at the dartboard. Like I said, we're just warming up. Let's throw those 5 darts. So we've got poor accuracy. So the poor accuracy means that we are far from the accepted value. And in this case, we're throwing darts. You want right, to be close to the bullseye if you're throwing darts. So here are my darts. Here's 1, here's 2, here's 3, here's 4, and let's say here's the 5th one. So we have poor accuracy, right? We are far from the bullseye, the desired target, what we're trying to get, but we have good precision in that all of my darts are relatively close together. The next round of darts, you've got 5 more darts to throw, and this time you have poor accuracy and poor precision. So what would this like? Poor accuracy, we're not close to the bullseye, and poor precision, our darts aren't close together. So I throw 1, I throw 2, I throw 3, I throw 4, I throw 5. I may even miss the dartboard. So this would represent poor accuracy and poor precision. We're not very close to the bullseye, and right, our darts are not clustered together. They're not very close together. The last one, and this is the ideal scenario, right? You've warmed up now. You've played 3 games of darts. You've got the 5 more darts to go. Yeah, now you have good accuracy and good precision. So what that would look like, 1, 2, 3, 4, and 5. So all of your darts are very close to the bullseye or in the bullseye. You're very accurate, and all those darts are clustered together. You have very good precision. And that's what we'd ideally like to see in science. You'd like to have all of your measurements be very close to the accepted value and be very precise in that all of the measurements are all around the same number. And sometimes students ask, when we're covering this example, what about if you have good accuracy and poor precision? And that's kind of hard to demonstrate in this example, because good accuracy, you want to hit the bullseye. But poor precision means your data is scattered all over the place. And so in this example, it'd be hard to see on an individual data set of 5 darts, but you could see by an average. So if things averaged out to be accurate, right, that's possible. But in the game of darts, it's kind of hard to represent an example like that. But this is what we're talking about when we're talking about accuracy and precision. Accuracy, how close are we to the bullseye? And then precision, how close are all of your measurements to each other?